Hello, I'm Dr. Ron Eaglin, and this is COP 3530, Data Structures, and today we're going to talk about trees, and specifically we're going to talk about binary trees. And even though our lecture says this is trees part 2, we're going to start trees from the beginning. Part 1 was a programming presentation, which was done on the computer, so part 2 is just going back through some of the theory that goes with trees. What I want you to be able to do is I want you to understand what a tree is. And remember, when we're talking any of these data structures, we're talking about an abstract data type, which basically is the concept, and we're talking about the implementation of how you do it. And of course, and you know this, any abstract data type can be implemented in many different ways. So we're going to look at some implementations of, in this case, binary trees. We are going to look at trees other than binary trees later, but right now we're just going to stick to binary trees. And you'll know what a binary tree here is in a minute. And why do we even care? Of course, that's one of the things that you really want to know is, what do you need to know trees for? So first, let's get down to the definition of a tree. So, an empty structure is an empty tree. So nothing is still a tree. That's amazing. So if you have nothing on your paper, you've still got a tree. But the second part of the definition, which says that it's a tree if you can trim its branches and the branches are still a tree. Okay, I know that sounds like a good recursive definition because it is a good recursive definition. But the bottom line is that actually works. And if it meets 1 and 2, it is a tree. Now, don't get caught up in this concept of the roots and the children and the branches doing this. It's not that hard. If you look at something, it's pretty obvious of whether it's a tree or not. So we do know that the empty structure is still a tree, or a node all by itself is a tree, because if I trim off all its children, it's still a tree. Okay, it's either going to be a single node or it's going to be no node, which are both trees. But what we're talking about is really some sort of hierarchical thing that you branch off. And in binary trees, there's 2 branches. And other types of trees, there can be more than 2 branches. But if you trim off those branches, it still is, everything that you've made is still trees. And of course, the branches can go further and further. And in a tree, you've got this concept of the height of the tree. So the empty tree is 0, height is 0. The single node is a height of 1. When you have just children underneath a single thing, there's a height of 2. It's not that hard to count the height of a tree, really straightforward. So let's talk the binary tree. The binary tree is a special case of trees. It's a very important special case because it's really one of the most used special cases of a tree. And in a binary tree, you have a root or a parent. We can call it both, but the root is the very top level parent. You have arcs, which connect to nodes. There's always 2 nodes. We usually say a left node and a right node. We can call them the left child and the right child. We can call them the left or the right. You're going to see a lot of different ways that it's, but I usually like to call them the nodes that are the child nodes of any of the parents will be the left and the right. So I may say left child and right child, or I may just say the left and the right. One of the properties of the tree is that you're always going to have a way of getting from the root to any of the individual nodes just by tracing down, and it's not going to be some really difficult trace. That is called a path. So getting from the root to any node, you've got a unique series of nodes and arcs that you pass through, and that's a path. Again, nothing, don't get, oh wow, is this hard? No, it's not. It really is that easy. Now, don't believe me, it's going to get a little bit more complex as you work a little bit later on. So let's look a little bit about how we can implement this binary tree. Well, as you've looked at the tree, you should be able to say, well, I'm used to things like lists, and a list might have a previous and a next, or it might just have a next, and it usually has some content. Well, in the case of a node, you've got a left and a right and some content. And you could also keep track of the previous. I could have this dot parent. So I could have a pointer to the parent. But in a binary tree, the 2 things that you've got to have are a point to the left child and a point to the right child, which I usually just call left and right. And to make the tree useful, you typically also want to have the tree nodes be able to hold some sort of content. So those are simply pointers to other nodes. And then when you actually implement the tree itself, the binary tree, because that was an implementation of the nodes of the tree simply needs to keep a pointer to the root. And if the nodes are designed so they have pointers to the children, once you got the root, you've got everything. So a binary tree is simply a pointer to an individual node, but the nodes are defined as having those left and right children. Again, it looks easy because it actually is easy. Now, with that simple definition, there are tons of things that we're going to be able to do. And we're going to actually have multiple lectures going over a lot of things that you can do. One of the things that you do in a tree is you traverse the tree. You need to get to specific individual nodes in the tree. So the way that you organize the tree is going to be important. Traversal is also going to be important. So you've got this concept of breadth first traversal and depth first traversal. And when I say breadth first and depth first, it doesn't mean that there's only one way to do breadth first and one way to do depth first. There's multiple ways, but the concept of breadth and depth are always going to be the same. So in breadth first traversal, you simply start at the top node, and that's the first one. Then you go to the next level, okay, and then you traverse those, then you go to the next level, then you traverse those, then you go to the next level, and you traverse those. So in this case, a breadth first traversal is going to give you 15, which is one that you would visit, then the next level. Okay, those are going to be the ones that actually come off of the top node, 4 and 20, and then to the next level, which is going to be 1, 16, and 25. We don't do a lot of breadth first traversals. We normally do depth first traversals. Because if you look at the way that I designed the nodes in the previous example, it's much easier to go down breadth first, or depth first to get to something. And when you get to depth first, you're going to start talking about something called, in a sense, it's going to be LRV, or LVR, or VLR, or VRL. What is that? Well, L stands for left, R stands for right, and V stands for I visited it. So in the case of an LVR, depth first traversal, what you're going to say is, I'm at the top node. I'm there, but I'm not going to mark it as visited. From there, I'm going to go left. I go to the left and I get to 4. And if 4 has a node to the left, I'm going to go to that node. Well, once I get down to that node, which is the 1, I don't have a left, I don't have a right, so I can't go left. I'm going to now say it's visited. So the first node in this tree example that's visited in an LVR is node 1. Now I'm going to go back up the tree to 4. And because it's LVR, when I get to 4, I'm going to say I visited 4. And when I go back up to the 15, because now I'm going back up the tree, it's LVR, I'm going to say I visited the 15. Now I'm going to go right and do exactly the same thing. So I go down again, I'm going to the right, I hit the 20. Well, I'm on the R. Okay, the 15 is visited, but now when I get to the 20, I'm not going to mark it as visited. I'm going to go left if I can. I go left, I hit 16, I come back up, I go back to 20. Now I'm going to mark it as visited, and then I'm going to go to 25. So your sequence is 1, 4, 15, 16, 20, 25. You should be able to follow that. If I say, what is the traversal of a depth first traversal? What's the order of items visited in a depth first traversal in LVR? This is the order. And of course, there are other ways to do this. So let's look at this concept of, in this case, an LRV. What am I doing? What would a function look like that was implementing LRV? Well, it's not, again, it's not that hard. I'm going to go, if I've got a left, I'm going to traverse the left. If I've got a right, I'm going to traverse the right, and then I'm going to mark myself as visited. Because once I traverse the left and I traverse the right, it is going to come back to me. It's a recursive algorithm. It's always going to return to me. Okay, and if I got called by somebody else, I'm going to return back to that one. L equals left, R equals right, V equals visited. Okay, so those are different ways to approach the depth first traversal. And it is important because the order of the things that come back in LRV, LVR, and VLR are all going to be different. Now, if you look really close here, you can spot my mistake. I threw a mistake in there, and let's see if you can look at that and spot it. My depth first traversal from LVR, okay, if I did LVR, it was the one from before, so that one was correct, so you know I didn't make a mistake there. But let's look at the depth first, LRV. Okay, LRV means I'm going to mark it visited as last. So what should always be the last one? The root should always be the last node in the traversal. So, well, that works out because if you look at my LRV, you'll notice that 15 is in there. But if you look at it closer, you can also notice that I put 16 in twice. Well, one of those 16s is wrong. Can you tell which 16 is wrong? Okay, look at it. If you noted that the second 16 in the LRV was incorrect, it should be 20, then you definitely now have this concept of how to do LRV traversal. If you can do LRV traversal, you can do LVR, and if you can do LVR, you can do VLR. And if you can do VLR, you can also do VRL because it's really just the same thing as a mirror image. Simple, straightforward. Also notice that when I put this up there, my node is actually very well organized. The left is always less than the parent, and my right is always more than the parent. That's actually another concept of trees that you're going to need to understand. How do we organize putting the nodes in? We're going to get to that later. So, later is now. Sorted trees. That tree that you saw before in the previous slide had a logic. The logic was, if the new node is less than the current node, I'm going to go to the left. If the current is greater, I'm going to go to the right. And then I'm going to go down to the next node, and I'm going to do the same thing again until I find a place to put my node. The one thing that this does, which we're going to look at later, is it can give you trees that are grossly imbalanced. They can have like very little over to the left and very much to the right. And if you've ever seen trees in the real world that looks really imbalanced, we don't want imbalanced trees. We're going to have to figure out how to balance them, but let's worry about how to balance them later. So if you've got this, how would you do this? Okay, so you've got a tree and you need to insert a 2. Well, okay, you get to the 15, the 2 is less than 15, go to the left. You get to the 4, okay, it's less than the 4, you go to the left. You get to the 1, it's greater than the 1, you go to the right. And you drop that node right there. Now, what if it actually had equaled one of those? Well, there's a lot of different ways to deal with that. Usually if I've got nodes, well, many times when you're using trees, the nodes are going to be unique and you never have to worry about a node actually equaling another node. But if you don't have a uniqueness property that's in the node, you can say, well, you know what? They're nodes. I control them because I built it. I built the tree. I can just have a counter that says, okay, if I drop another 1 on there, when I get to the node that's the 1, I just increment a counter, and now that I know that there's 2 1 nodes sitting in the same spot, the node itself just keeps a counter of how many 1 nodes were dropped. Okay, that's actually a very good and valid technique. But the problem here is this tree is starting to get a little bit out of balance. Now I've got the left side, which is this long line, and the right side, which actually is balanced out pretty nicely. I need to be able to fix that. So we're going to have to talk about how to keep these things balanced. Deletion, well, in deletion, and as you saw, insertion, well, that was pretty easy to do, you know, left or right. Deletion is not necessarily non-trivial. Okay, it takes a little bit of movement of pointers. It's not, in this case, extremely hard, because what you would do is, suppose you want to delete the 20 here. Well, if you deleted the 20, you would just move the 16 up to the 20's position because it's between 15 and 25, and then the 16 would have a right pointer to the 25. Okay, but it did require some motion that is a little bit more challenging, some decisions that makes it more challenging in the insertion case. And voila, that's what you should get if you did the deletion of the 20 from the node. And again, realize it wasn't non-trivial because you did have to move something. You couldn't just go in and delete something out. Pointers had to be changed to make it work. It wasn't hard, but it's still something that you had to do. What do we use these for? Trees are one of the most used data structures in all of computing. Well, it is kind of the de facto standard for dealing with things that you need to be able to search, especially if you need to be able to dynamically keep things up to date and searchable. Trees are the way to go. So you've got things like binary space partitions, which are used in 3D games. And those are ones we might talk about a little bit later, but they're also definitely ones that you want to look up and see how that's worked, because everything that you do on a computer requires some sort of decision. So let's suppose you've got a 3D game, and the 3D game actually in the computer has to render some physical environment. And in rendering that physical environment, it has to make decisions of what to render first. Well, the trees give you a great capability of being able to make those decisions rapidly and do the implementation of that actually 3D interface. Routers, databases, scheduling systems, all of those things are things that you use binary trees for, and they're essentially everywhere in the computer. So hopefully you understand the concept of a tree, you understand the abstract concept of what a tree is, and you do at least now know one or multiple implementations of how to put a tree together, and then some algorithms of things that you can do with a tree, primarily traversal, but also insertion and deletion are things that you have to be able to do. And you can describe the use. What are these trees actually used for, and how are they important to the whole concept of IT and computer science and programming? If you've got that, you've done quite well, but we're going to move on to some more advanced things soon. So this is Dr. Ron Eaglin checking out from Daytona State College. Thank you very much.